Far beyond Earth, beyond Mars, beyond Jupiter, past the bright rings of Saturn, there is a small frozen moon that almost nobody cared about for most of human history. Its name is Enceladus. At first glance, it does not look like the kind of place that could change science forever. It is not huge like Titan. It is not volcanic like Io. It is not famous like Europa. It is only about 500 kilometers wide, small enough that if you placed it across the United States, it would not even cover the full width of a single major state. From Earth, it appears as nothing more than a tiny dot of light hidden in the glare of Saturn's magnificent rings. But sometimes, the universe hides its biggest secrets inside the smallest places. When Enceladus was discovered in 1789 by William Herschel, nobody saw an ocean, nobody saw geysers, nobody imagined chemistry, heat, or possible life. They saw a moon so faint that it required one of the most advanced telescopes of its age just to confirm it existed. For nearly 200 years, Enceladus remained a quiet mystery, a frozen speck orbiting a giant planet almost 1 billion miles from the Sun. Astronomers knew it was there, but they did not know what it was doing. And that is the first strange thing about this moon. It was always hiding in plain sight. If you were standing on the surface of Enceladus, the Sun would not feel like the Sun we know. It would look like a brilliant star, distant and weak. The sky would be black. Saturn would dominate the heavens, enormous, terrifying and beautiful, hanging above the horizon like a god made of storms and rings. The ground beneath your feet would be ice, brighter than almost anything else in the solar system. Enceladus reflects most of the sunlight that hits it, which means its surface is fresh, clean, and young-looking. That detail sounds simple, but it is actually one of the first clues that something was wrong. Old icy worlds are supposed to be scarred. They should be covered in craters from billions of years of impacts. They should look ancient, damaged, and dead. But Enceladus did not fully match that picture. Even before spacecraft reached Saturn, scientists noticed something unusual. Enceladus was orbiting inside Saturn's E-ring, a faint and wide ring made of tiny, icy particles. The question was simple but disturbing. Where was that material coming from? At first, nobody had a clear answer. Maybe small impacts were knocking ice off Enceladus. Maybe the ring material came from somewhere else. Maybe it was just coincidence. But space rarely gives coincidences without a reason. The closer scientists looked, the more suspicious this tiny moon became. It was too bright. It was too clean. It was sitting exactly where icy particles were most concentrated. It was almost as if Enceladus was not just moving through the ring, but feeding it. That idea sounded impossible. A moon this small should have frozen solid long ago. It should not have enough internal heat to do anything dramatic. It should not have volcanoes. It should not have an ocean. It should not be active. But science often begins with the phrase, "that should not be happening." This is what makes Enceladus so powerful as a story. It begins as nothing, a tiny ice ball, a background object, a footnote in Saturn's system. But underneath that ice, something was happening that no telescope on Earth could see. For centuries, Enceladus kept it secret. It circled Saturn silently, reflecting sunlight, hiding cracks, hiding heat, hiding an ocean that may have been moving beneath its frozen shell for millions or even billions of years. And then humanity finally sent machines close enough to look. The first great reveal did not come from a telescope. It came from Voyager. Part 2. Voyager sees a moon that should be dead, but isn't. In the early 1980s, the Voyager spacecraft flew through the outer solar system and changed our view of everything. Before Voyager, the moons of the outer planets were mostly mysterious points of light. After Voyager, they became worlds. Suddenly, humanity saw volcanoes on Io, strange terrain on Europa, storms on Jupiter, rings around Saturn, and icy moons that looked far more complicated than anyone expected. When Voyager approached Saturn, Enceladus was not the main attraction. Titan was the celebrity moon. Saturn's rings were the visual masterpiece. Enceladus was small, distant, and easy to underestimate. But when Voyager's images came back, scientists noticed something that did not make sense. Parts of Enceladus looked ancient and cratered, exactly as expected. But other regions looked shockingly smooth. Some areas had very few craters at all. That meant the surface had been renewed sometime in the moon's past. Something had erased old scars and replaced them with fresh ice. On a world this small and cold, that should have been nearly impossible. A dead moon keeps its scars. Enceladus was hiding them. This was the second major clue. Smooth terrain means activity. It means the surface has changed. It means something from below may have pushed upward, cracked the crust, flooded old areas with fresh material, or reshaped the ice. Scientists began asking a dangerous question. Could Enceladus still be geologically active? At first, that idea seemed too bold. Enceladus was tiny. Tiny worlds lose heat quickly. Earth is geologically alive because it is large, has radioactive decay, internal heat, plate tectonics, and a molten interior. Enceladus had none of that on the same scale. It should have become a frozen rock long ago. But the images were not lying. Something had happened there. Then came the E-ring mystery again. Voyager helped strengthen the suspicion that Enceladus was connected to Saturn's broad, faint E-ring. The moon was located right in the densest region of that ring. That meant icy particles around Saturn were somehow being supplied, refreshed, or maintained near Enceladus. But how? Imagine scientists looking at these images in mission control. They are not seeing aliens. They are not seeing life. They are not even seeing liquid water directly. What they are seeing is more subtle and more haunting. A moon that should look old looks young. A moon that should be inactive may have changed recently. A moon sitting in a ring of ice particles may be responsible for creating that ring. And yet Voyager could not stay. It was not designed to orbit Saturn. It was a flyby mission. It passed through, took its images, collected its data, and moved onward into deep space. Voyager gave humanity a glimpse, but not an answer. That is what made Enceladus so frustrating. It showed just enough evidence to become suspicious, then disappeared back into distance. For years after Voyager, scientists had to work with limited images and unanswered questions. Was Enceladus active now, or had it only been active in the past? Was there liquid water beneath the ice, or only frozen layers shifting slowly? Was the E-ring truly coming from Enceladus, or was that connection misleading? These questions mattered because liquid water changes everything. Anywhere scientists find liquid water, they start thinking about habitability. Not life immediately, but possibility. And possibility is enough to reshape a mission. Voyager had transformed Enceladus from a boring ice moon into a target. It was no longer just another small satellite. It became a mystery world, a moon that seemed to whisper, "Come back and look closer." And decades later we did. That return would be called Cassini. Part 3. Cassini enters Saturn's kingdom. Cassini was not just another spacecraft. It was one of the most ambitious planetary missions ever built. Its job was to enter Saturn's system, study the planet, examine the rings, observe its moons, and carry the Huygens probe to Titan. It was a machine designed to survive years in deep space, travel billions of kilometers, and operate in one of the most complex environments in the solar system. When Cassini launched in 1997, it began a long journey that required patience, precision, and almost unbelievable engineering. It could not fly directly to Saturn with simple fuel power. Instead, it used gravity assists, swinging around planets to gain speed like a stone thrown across the solar system using invisible gravitational slings. Venus helped it, Earth helped it, Jupiter helped it. And finally, after years of travel, Cassini reached Saturn in 2004. Imagine that moment. A spacecraft built by humans arrives at a giant planet surrounded by rings wider than worlds. Saturn is not just a planet, it is a system. It has moons, dust, ice, radiation, storms, and gravitational complexity. Cassini entered that kingdom like a silent explorer entering a cathedral of ice and gas. At first, Enceladus was still not the main star. Titan demanded attention because of its thick atmosphere and possibility of lakes and complex chemistry. Saturn's rings demanded attention because they were beautiful and scientifically rich. But Enceladus was there, quietly waiting, a small moon with old Voyager mysteries attached to it. Then Cassini began looking closer. The images revealed a world more complex than expected. Enceladus was not just a smooth white ball. It had fractures, ridges, plains, cracks, and strange terrain. Some regions were heavily cratered, suggesting ancient surfaces. Other regions appeared fresh and young. The contrast made the moon look like a frozen world with a violent past, or possibly a violent present. Then came the South Pole. The South Polar region of Enceladus looked unlike anything scientists expected. Long, dark fractures stretched across the ice. These became known as tiger stripes. They were not random scratches. They looked organized, active, and warm compared with the surrounding surface. Infrared measurements showed excess heat coming from this region. That was alarming. A tiny, icy moon should not have a warm south pole. Scientists began to realize they were not just looking at old geological scars. They might be looking at vents, openings, weak points in the ice where material from below was escaping. But escaping from what? A warm ice layer? A pocket of liquid water? A hidden sea? Then Cassini saw the impossible. Something was erupting from Enceladus. At first, the images looked almost unreal. Faint streams of material were rising from the South Pole and stretching into space. These were not clouds in an atmosphere. Enceladus barely had one. These were jets, icy geysers blasting water vapor and particles into the vacuum. That single discovery changed the mission. Suddenly, Enceladus was no longer just interesting. It became urgent. Because if material was being thrown into space from below the surface, then Cassini did not need to land. It did not need to drill. It did not need to melt through kilometers of ice. The moon itself was delivering samples into space. This was one of the greatest gifts nature could offer scientists. An underground ocean, if it existed, was leaking. Cassini could fly through the plume and taste it, but doing that required risk. Spacecraft do not casually dive close to icy moons at high speed. Every maneuver matters. Every trajectory has consequences, but the possibility was too important to ignore. NASA adjusted Cassini's path and prepared for close flybys. The mission had entered a new phase. Cassini was no longer only observing Saturn, it was hunting for signs of life. Part 4. The plumes that stopped scientists cold. The discovery of Enceladus's plumes was one of those rare scientific moments where a small object suddenly becomes enormous in meaning. In the images, the geysers looked delicate, almost ghostly, like pale fountains rising from a frozen desert, but physically they were violent. Water vapor, ice grains, salts, and organic material were being launched from the South Pole into space at high speeds. This was not just surface frost blowing away. This was internal activity. That difference is everything. If Enceladus was ejecting water from inside itself, then something below the crust had to be warm enough, active enough, and pressurized enough to drive those eruptions. Scientists began connecting the clues: smooth terrain, fresh ice, E-ring particles, tiger stripes, heat, plumes. The picture was forming. Enceladus might have a subsurface ocean. And not just any ocean, a global or regional ocean trapped beneath an ice shell, warmed by tidal forces, interacting with a rocky core and escaping through cracks near the South Pole. The tiger stripes became central to the mystery. These long fractures seemed to act like valves or vents. As Enceladus orbited Saturn, gravitational forces flexed the moon. That flexing may open and close cracks, allowing water vapor and ice particles to escape. The moon was being squeezed and stretched by Saturn's gravity, and that motion may have kept its interior warm. This is where the story becomes almost cinematic. Picture Enceladus orbiting Saturn every 33 hours. Each orbit, Saturn's gravity pulls at it. The moon bends slightly. Its icy shell creaks. Deep below, water moves through rock. Heat rises. Pressure builds. Then, through fractures at the South Pole, the hidden ocean breathes into space. That is what the plumes are. They are the breath of Enceladus. For scientists searching for life beyond Earth, this was breathtaking. Usually, ocean worlds are locked away. Europa has an ocean, but it is beneath ice. Titan may have a subsurface ocean, but it is deeply hidden. To study these places directly, you might need landers, drills, cryobots, or submarines, technologies that are extremely difficult. But Enceladus was different. It was throwing ocean material into space for free. Cassini could fly through it. This changed the question from does Enceladus have an ocean to what is inside that ocean? And that is when the real suspense began. Because water alone is not enough. Life needs ingredients. It needs chemistry. It needs energy. It needs stability. It needs time. So Cassini's job became clear: fly through the plumes and analyze what they contain. The spacecraft carried instruments capable of detecting particles and molecules. It could measure ice grains. It could identify chemical signatures. It could help scientists understand whether the plume material came from shallow ice, deep water, or hydrothermal processes at the ocean floor. Every flyby became valuable. Every pass through the plume was like dipping a tiny scientific spoon into an alien sea. And then the results started coming back. Water was there. Salts were there. Organic molecules were there. Hydrogen was there. Silica particles suggested water-rock interaction. These were not random ingredients. They pointed toward a chemically active ocean. The terrifying implication was this: Enceladus was not simply wet. It might be habitable. That word changed everything. Habitable does not mean inhabited. It does not prove life. But it means the environment may have the conditions life needs. And in the search for life beyond Earth, that is one of the most powerful words in science. Cassini had found a place where the impossible seemed possible. A frozen moon near Saturn was erupting water into space, and inside that water were clues that pointed beneath the ice. Part 5. Flying through an alien sea. Cassini never landed on Enceladus. It never touched the ice. It never drilled into the crust. It never saw the ocean directly. And yet, in one of the most extraordinary shortcuts in space exploration history, it sampled material from that hidden ocean by flying straight through the plumes. Imagine the scene. Cassini is moving at incredible speed through the Saturn system. Ahead is Enceladus, bright white, silent, and frozen. From its south pole, jets of material are spraying into space like fountains from an invisible sea. Mission controllers on Earth know that if they guide Cassini close enough, the spacecraft can pass through that plume and collect chemical evidence from beneath the surface. But this is not simple. Cassini is not flying through mist on Earth. It is traveling through space at high velocity, crossing streams of icy grains and vapor. Its instruments must capture and interpret particles that slam into detectors at enormous speeds. The data will not arrive as a simple message saying "life found" or "ocean confirmed." It will arrive as signals, mass spectra, patterns, fragments, chemical fingerprints that scientists must decode carefully. This is where the mystery becomes scientific detective work. Cassini's instruments detected water vapor, carbon dioxide, methane, ammonia, salts, and organic compounds. Some particles suggested the ocean was salty, similar in some ways to Earth's oceans. That mattered because salts indicate liquid water interacting with rock. The moon was not simply melting clean ice. It likely had an ocean touching a rocky core. Then came hydrogen. Hydrogen was one of the most exciting discoveries because it can be used as a chemical energy source by microbes on Earth. In deep-sea environments on our planet, certain organisms do not depend on sunlight. They survive through chemistry. Around hydrothermal vents, hot mineral-rich water rises from the seafloor, creating energy-rich reactions. Entire ecosystems live there in darkness. That comparison shook scientists. Because if Enceladus has hydrothermal vents, then it may have one of the same types of environments that helped life begin on Earth. This does not mean fish, plants, or intelligent aliens. The most realistic possibility is microbial life. Tiny organisms living in the ocean, perhaps near warm vents, feeding on chemical energy. But even one microbe would be the biggest discovery in human history. It would mean life started twice in one solar system. It would mean biology is not unique to Earth. It would mean the universe may be far more alive than we ever imagined. The beauty of Enceladus is that it checks the boxes one by one. Liquid water? Yes. Energy? Likely yes, through tidal heating and hydrothermal reactions. Chemistry? Yes, including organic molecules and essential elements. Time? Possibly, if the ocean has lasted long enough. But Cassini also left scientists with frustration. The spacecraft was never designed as a dedicated life detection mission for Enceladus. It was built before anyone knew these plumes existed. Its instruments were powerful but limited. It could detect chemistry but not directly confirm living cells. It could show habitability, but not prove biology. That is the heartbreak of Cassini. It reached the edge of the answer, but could not cross it. As the mission continued, every plume flyby became more important. Scientists kept asking, are these molecules formed by ordinary chemistry, or are they hints of something more? Are the organics simple building blocks, or part of a deeper chemical system? Is hydrogen being produced by water-rock reactions in hydrothermal vents? Is the ocean stable? Is there enough energy for life to survive? Cassini gave clues, not final proof. And then, in 2017, the mission had to end. Low on fuel, Cassini became a contamination risk. If NASA lost control, the spacecraft could someday crash into Enceladus or Titan, possibly carrying Earth microbes. To protect these worlds, scientists chose a dramatic ending. Cassini was sent into Saturn's atmosphere, where it burned up like a messenger, sacrificing itself to protect the mystery it had discovered. But before it died, Cassini changed Enceladus forever. It transformed a tiny icy moon into one of the most promising places to search for alien life. And the strangest part is this: even after Cassini was gone, its data kept speaking. Part 11, Cassini's Final Sacrifice. By 2017, the Cassini spacecraft had already exceeded almost every expectation humanity had placed upon it. What began as a mission to study Saturn and its moons had evolved into one of the greatest scientific expeditions in history. For 13 years, Cassini traveled through the Saturn system, watching storms larger than Earth swirl across the gas giant, mapping the rings in extraordinary detail, exploring Titan's methane lakes, and transforming Enceladus from a forgotten ice moon into one of the most promising places to search for alien life. But every spacecraft carries a hidden clock: fuel. Cassini was dying. The spacecraft did not run on unlimited energy. To maintain its orbit, adjust its trajectory, and point its instruments correctly, Cassini depended on small bursts from onboard thrusters. Over time, that fuel supply dwindled. Engineers knew the end was approaching long before the public did. The mission team faced a terrible decision. What should humanity do with a spacecraft that had discovered worlds that might support life? At first, it might seem obvious. Leave Cassini drifting harmlessly through space. But the Saturn system is not empty. It is crowded with moons, gravitational interactions, and orbital chaos. Over enough time, an uncontrolled spacecraft could eventually crash into a moon. And that possibility terrified scientists, because Cassini came from Earth. Even after years in deep space, microscopic Earth microbes might still survive inside protected parts of the spacecraft. If Cassini accidentally contaminated Enceladus or Titan, humanity could destroy the very thing it was searching for. Imagine future missions discovering microbes on Enceladus, only to realize later they came from Earth contamination. The scientific consequences would be catastrophic. To protect these worlds, NASA chose a dramatic ending. Cassini would die deliberately. The final phase of the mission became known as the grand finale. Engineers designed a series of daring orbits that would send Cassini diving repeatedly between Saturn and its rings, passing through regions no spacecraft had ever explored before. Even at the end, Cassini continued gathering extraordinary data. Then came the final command. On September 15, 2017, Cassini aimed itself towards Saturn's atmosphere. Imagine the loneliness of that moment. A machine built by humans, launched decades earlier, billions of kilometers from Earth, plunging into a giant planet it had spent years exploring. No rescue, no return, no landing, just descent into fire. As Cassini entered Saturn's atmosphere, the spacecraft began struggling against increasing drag. Small thrusters fired continuously, trying to keep the antenna pointed toward Earth so the final data stream could continue. For a brief time, Cassini fought to survive. But Saturn is enormous. Its atmosphere thickened rapidly. Eventually, the thrusters could no longer compensate. The spacecraft lost stability. Communication weakened. Then the signal vanished forever. Cassini was gone, destroyed to protect possible life on Enceladus. That fact alone feels almost poetic. Humanity sacrificed one of its greatest robotic explorers because the worlds it discovered had become too important to risk contaminating. Think about how extraordinary that is. A tiny moon orbiting Saturn changed the way we think about life so profoundly that we destroyed our own spacecraft to preserve its purity. And perhaps the most emotional part of the story is this: Cassini died without fully answering the question it raised. It proved Enceladus was active. It proved an ocean existed. It detected organic chemistry. It found hydrogen, salts, and evidence of hydrothermal activity. But it could not directly prove biology. The spacecraft reached the edge of the greatest discovery in human history and stopped just short of confirmation. That unresolved mystery transformed Cassini's ending into something larger than a normal mission conclusion. It became a handoff. A message to future generations: we found something extraordinary. Now you must continue. And strangely, Cassini's death was not really the end at all. Because once the spacecraft disappeared into Saturn's atmosphere, scientists turned back toward the mountain of data it had already sent home. And hidden inside that data were discoveries nobody had fully understood yet. Part 12. The data scientists still haven't finished reading. Most people imagine space missions ending when the spacecraft dies. In reality, that is often when some of the most important discoveries begin. Cassini spent 13 years collecting enormous amounts of information: images, spectra, particle measurements, magnetic field data, thermal maps, chemical signatures. The spacecraft gathered so much material that scientists could not fully analyze it all before the mission ended. Even today, researchers are still studying Cassini's observations. That detail matters because science evolves. The instruments on Cassini never changed after launch, but human understanding did. Computer models improved, laboratory experiments improved, Analytical software became more advanced. Artificial intelligence and machine learning techniques allowed researchers to revisit old datasets with fresh eyes. And when they did, Enceladus became even stranger. One of the biggest challenges involved interpreting mass spectrometry data from the plumes. Cassini's instruments identified molecules by smashing particles apart and measuring the fragments. But molecules behave differently depending on impact speed, ionization energy, and environmental conditions. Early analyses provided valuable information, but scientists knew uncertainties remained. Then newer techniques allowed researchers to simulate how complex molecules break apart during high-speed impacts. Suddenly, patterns inside the old data began making more sense. Some molecules detected in the plumes were far more complex than originally believed. Researchers identified larger carbon-bearing compounds associated with advanced organic chemistry. Nitrogen-containing compounds appeared. Oxygen-rich structures emerged. Ring-shaped molecules and complex hydrocarbons became easier to distinguish. This was not simple chemistry anymore. Enceladus appeared chemically rich. The implications became deeply unsettling, because chemistry naturally becomes more interesting over time. Given enough energy, enough reactions, and enough environmental stability, molecules can organize into increasingly complicated systems. On Earth, that process eventually led to biology. Scientists started asking whether Enceladus's ocean could support prebiotic chemistry, the stage before life emerges. Could molecules inside the moon already be assembling into increasingly complex structures? Could primitive metabolic systems exist there right now? Those questions pushed researchers into dangerous scientific territory. Not dangerous physically, but intellectually, because once you begin discussing possible biology, public imagination races ahead. Scientists remained cautious. Organic molecules do not equal life. Hydrothermal activity does not equal life. Habitability does not equal life, but the problem was obvious. Enceladus kept behaving like a place where life should be possible. Then came phosphorus. For years, this element remained frustratingly elusive. Scientists considered phosphorus essential because all known Earth biology depends heavily on it. DNA, RNA, ATP, and cell membranes all require phosphorus chemistry. Without phosphorus, Enceladus's habitability remained incomplete. Then researchers revisited old Cassini data and identified phosphorus-rich compounds likely originating from the ocean. That discovery was monumental. Now Enceladus appeared to contain all 6 key elements associated with life: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, schnapps, the full biological toolkit, and all of it was erupting into space from beneath the ice. Scientists also realized something else frightening. Cassini was never optimized specifically for detecting alien life. Remember that. The spacecraft was designed before anyone knew the plumes existed. Its instruments were not purpose-built to search for microorganisms or direct biosignatures. Despite that limitation, Cassini still found evidence for habitability far beyond expectations. Imagine what a dedicated mission could discover. Future spacecraft could carry advanced biological analyzers, high-resolution molecular detectors, amino acid sequencing tools, and even microscopes capable of examining plume particles directly. Cassini may have only scratched the surface. The mission's legacy became larger with every passing year because its data refused to stop revealing surprises. Scientists began comparing Enceladus to a locked library where humanity had only translated the first few pages. And perhaps the most haunting idea is this: the evidence for life may already exist somewhere inside Cassini's data. Buried within millions of measurements, there may be patterns nobody has recognized yet. Maybe certain molecular ratios hint at biological processes. Maybe unexplained chemical imbalances indicate metabolism. Maybe subtle structures in the plume particles point towards something alive. The possibility keeps researchers awake at night, because humanity may already possess evidence of alien biology and simply lack the tools or understanding to recognize it fully. That is why Enceladus still dominates astrobiology conversations nearly a decade after Cassini's death. The mission ended, but the mystery never did, and then another instrument entered the story. A telescope far more powerful than anything Cassini carried. The James Webb Space Telescope. Part 13. James Webb sees the moon breathing. When the James Webb Space Telescope launched, most people focused on distant galaxies, black holes, and the early universe. Webb was expected to look billions of years into the past, capturing ancient light from the first stars and galaxies. Few people imagined it would also transform our understanding of a tiny moon orbiting Saturn. But that is exactly what happened. Even after Cassini's destruction, scientists remained desperate to monitor Enceladus. They wanted to know whether the plumes were temporary or long-lasting. Were the eruptions weakening, strengthening, changing over time? Could the moon maintain activity for millions of years? Cassini could no longer answer those questions. Then Webb turned its mirrors towards Saturn. What it saw shocked researchers. Enceladus was still erupting enormous plumes into space. Not only that, the plume appeared vastly larger than expected, extending thousands of kilometers away from the moon. Webb revealed a gigantic cloud of water vapor spreading through Saturn's system like smoke from a hidden fire. Imagine the scale of this. Enceladus itself is tiny, only about 500 kilometers across. Yet the plume stretched far beyond the moon, feeding Saturn's environment continuously. Webb's observations showed water spreading into a giant torus around the planet, replenishing Saturn's E-ring and altering the chemistry of the surrounding space. Enceladus was not just active. It was reshaping part of Saturn's entire system. Scientists estimated the plume extended roughly 20 times larger than the moon itself. That image alone became one of the most haunting visuals in modern planetary science, a frozen world breathing water into space. And that breathing appeared stable. That detail matters enormously. Because life requires time, short-lived geological activity may create temporary oceans or isolated chemistry, but biology often requires long periods of stability. Webb's observations suggested Enceladus's ocean system may have persisted far longer than scientists once believed. That possibility elevated the moon from potentially habitable to something even more psychologically powerful, a long-term ocean world. The longer Enceladus remains active, the greater the opportunity for complex chemistry to evolve. And Webb revealed another astonishing truth. Enceladus is the only known moon in the solar system that significantly affects the chemistry of its host planet. Its plume material spreads throughout Saturn's environment, interacting with magnetic fields, plasma, and radiation. Water molecules from Enceladus eventually become ionized, contributing to enormous plasma structures surrounding Saturn. In a strange way, this tiny moon leaves fingerprints across an entire planetary system. That realization changed how scientists viewed Enceladus physically and symbolically. It is not isolated, it is dynamic, alive with motion, chemistry, and interaction. Webb also reinforced one of the most emotionally important aspects of the Enceladus story. The moon is still active today, not millions of years ago, not in some ancient geological era. Right now, at this exact moment, as humans sit on Earth watching screens and cities glow beneath our atmosphere, a hidden ocean beneath Saturn's ice is erupting water into space continuously. That immediacy changes the emotional weight of the story, because Enceladus is not a fossil world, it is ongoing. Its ocean exists now. Its chemistry exists now. Its hydrothermal processes may exist now. And if biology ever emerged there, then alien life may also exist right now. Somewhere beneath kilometers of ice, beyond the rings of Saturn, an ecosystem may be surviving completely unnoticed by the universe around it. That possibility transformed Enceladus from a scientific curiosity into something almost mythic, a hidden ocean world whispering across space. And yet, the deeper scientists looked into Saturn's environment, the stranger the physics around Enceladus became. Because the moon was not only producing water, it was producing enormous electromagnetic disturbances stretching across space itself. Part 14. The strange plasma rivers around Saturn. Enceladus does not only influence Saturn through ice and water, it also changes the planet's electromagnetic environment in ways scientists are still struggling to fully understand. This part of the story feels less like ordinary astronomy and more like science fiction physics. When water particles erupt from Enceladus's plumes, they do not remain neutral forever. Radiation from the sun and energetic particles trapped in Saturn's magnetic field strip electrons away from some of the material. The particles become ionized, and once particles become electrically charged, strange things begin happening. Saturn possesses a gigantic magnetic field generated deep within the planet's interior. That field traps charged particles and creates a complex plasma environment stretching across space. When Enceladus injects water vapor into this system, the moon essentially feeds plasma into Saturn's magnetic domain. Imagine invisible rivers of charged particles flowing through space around Saturn. That is not an exaggeration. Scientists discovered enormous plasma structures extending outward from Enceladus. These structures, known as Alphan wings, behave somewhat like electromagnetic wakes trailing behind the moon as it moves through Saturn's magnetic field. The scale is difficult to comprehend. Some plasma waves stretch hundreds of thousands of kilometers across space. A moon only 500 kilometers wide creates disturbances thousands of times larger than itself. This shocked scientists because Enceladus was never expected to have such influence. Tiny moons are supposed to be passive objects orbiting giant planets, but Enceladus behaves almost like an engine injecting material and energy into Saturn's environment continuously. The moon is small physically, but dynamically it punches far above its weight. These plasma interactions also help scientists study the plume indirectly. By measuring changes in magnetic fields and charged particle flows, researchers can estimate how much material Enceladus ejects into space. And the answer is astonishing. Hundreds of kilograms of water escape every second. Imagine oceans breathing into vacuum continuously. Over time, that material spreads throughout Saturn's system, helping maintain the E-ring and interacting with radiation belts and magnetic structures. The entire environment becomes a giant interconnected system driven partly by a frozen moon. There is something deeply eerie about this idea. Because Enceladus does not simply orbit Saturn silently, it actively reshapes the space around it. In a sense, the moon leaves invisible fingerprints across the planet's magnetic field. And yet, despite decades of study, scientists still do not fully understand all the plasma structures surrounding Saturn. Some reflected waves and magnetic disturbances behave in unexpected ways. Researchers continue modeling these interactions, trying to understand how the plume, plasma, and magnetic field combine into such a massive system. This uncertainty is important because it reveals something often forgotten in documentaries. Enceladus remains mysterious. We know far more than we did 20 years ago, but enormous gaps remain in our understanding. We still do not know the exact structure of the ocean. We do not know the thickness of the crust everywhere. We do not know how stable the hydrothermal activity truly is. We do not know whether biology exists. And we certainly do not fully understand all the electromagnetic consequences of the moon's activity. That mystery gives Enceladus emotional power. Because it reminds humanity how much remains hidden, a tiny moon billions of kilometers away continues generating discoveries faster than scientists can explain them. And perhaps the strangest part is this. Humanity may have seen evidence of Enceladus's activity decades before Cassini arrived. The clues may have been sitting quietly inside old Voyager images all along, waiting for someone to notice. Part 15. The Discovery Hidden in Plain Sight. One of the most unsettling aspects of science is realizing how often humanity misses enormous discoveries simply because nobody expected them to exist. Enceladus may be one of the greatest examples of that phenomenon. For decades, scientists believed the moon was mostly frozen and inactive. Voyager's flybys hinted at geological activity, but the spacecraft lacked the detailed instruments and close observations needed to reveal the full truth. So humanity moved on. Attention shifted elsewhere. The mystery remained incomplete. Then Cassini arrived and changed everything by discovering the plumes. But years later, something extraordinary happened. An amateur astronomer named Ted Strike revisited old Voyager images of Enceladus and noticed something strange near the moon's edge. A faint feature appeared to resemble a plume. That realization sent chills through planetary scientists, because it suggested evidence of Enceladus's eruptions may have existed in Voyager data decades earlier. Humanity may have looked directly at the plumes in the 1980s without recognizing what it was seeing. Think about that carefully. The evidence was there, but nobody knew what they were looking for. This happens repeatedly throughout scientific history. Discoveries often remain invisible until a conceptual breakthrough changes perception. Before astronomers understood galaxies, spiral nebulae looked meaningless. Before plate tectonics, continents seemed unrelated. Before germ theory, microorganisms were invisible causes without explanation. Knowledge changes vision. Once Cassini revealed the plumes, scientists suddenly understood Voyager's strange hints differently. Smooth terrain, young surfaces, E-ring connections, possible faint ejecta in old images. The clues aligned retroactively. Enceladus had been whispering its secret for decades. Humanity simply failed to listen. There is something deeply human about that story. We like to imagine science progressing smoothly, but real discovery is often messy and psychological. People struggle to see beyond expectations. If scientists do not believe a tiny frozen moon can contain an ocean, then evidence supporting that idea may appear unimportant or invisible. Cassini succeeded partly because it arrived prepared to ask different questions, and now scientists wonder what else humanity might still be missing. Could other icy moons contain hidden oceans? Could strange signals inside old datasets point toward undiscovered phenomena? Could evidence for habitability already exist elsewhere in archived observations? Enceladus became a lesson in scientific humility. The universe is often stranger than our expectations. The rediscovery of possible Voyager plume evidence also changed how researchers think about future missions. If scientists had recognized Enceladus's activity earlier, Cassini itself might have been designed differently. More specialized life detection instruments could have been included. Sampling systems might have been optimized specifically for plume analysis. In some alternate timeline, humanity may already know whether life exists beneath the ice. That thought is both exciting and painful, because Enceladus sits right on the edge of one of the greatest discoveries imaginable, close enough to tempt us, far enough to deny certainty. And now, after decades of clues, missions, and revelations, humanity faces a new reality. We cannot ignore Enceladus anymore. The moon has become too important, which is why space agencies around the world are beginning to plan something extraordinary. A return to the hidden ocean beneath Saturn's ice. Part 16. Humanity plans the return. For years after Cassini's death, Enceladus existed in a strange state within the scientific world. Everyone agreed it was extraordinary. Everyone agreed it deserved more exploration, and yet no spacecraft immediately returned. Part of the problem is distance. Saturn is brutally far away. Depending on planetary alignment, reaching it can take 6 to 10 years, even with gravity assists. Every kilogram of equipment matters. Every maneuver matters. Radiation, fuel limitations, communication delays, and budget constraints all become enormous challenges. Sending a spacecraft to Saturn is not like sending one to Mars. It is an interplanetary commitment that can consume decades of human effort. But despite those obstacles, Enceladus refused to fade from scientific attention. In fact, the opposite happened. The more scientists analyzed Cassini's data, the stronger the argument became that humanity needed to go back. Conferences, papers, mission proposals, simulations, and engineering studies began focusing on one central idea. Enceladus may be the best place in the solar system to search for alien life. Not Mars, not Venus, not even Europa, Enceladus. Because nowhere else offers such easy access to subsurface ocean material. Europa likely contains a vast ocean, but its crust may be tens of kilometers thick, and Jupiter's radiation environment is horrifyingly dangerous for spacecraft. Titan is fascinating but chemically complicated. Mars preserves ancient history but may no longer be biologically active. Enceladus is different. Its ocean is erupting into space continuously. That means future spacecraft may not need to land or drill immediately. They can fly through the plumes repeatedly, collecting samples with far more advanced instruments than Cassini ever carried. Scientists started designing mission concepts around this incredible advantage. Some proposed orbiters dedicated entirely to plume analysis. Others suggested flyby missions capable of passing through the geysers multiple times at lower speeds than Cassini, improving sample quality dramatically. Advanced mass spectrometers could identify amino acids, isotopic patterns, fatty acids, or even direct cellular fragments. Imagine a spacecraft crossing the plume and discovering unmistakable biological signatures. The announcement would instantly become the most important scientific event in human history. But many researchers want more than flybys. They want to land. Landing on Enceladus would be terrifyingly difficult. The surface is icy, uneven, and dangerously cold. Gravity is weak, making descent tricky. The South Polar region contains fractures and active vents that could destabilize landing systems. Yet despite those risks, mission planners continue developing concepts. One proposal involves landing near the tiger stripes to directly sample freshly deposited plume material. Another suggests autonomous laboratories capable of heating ice samples and searching for organic chemistry on site. And then there are the truly ambitious ideas. Cryobots, robotic probes designed to melt downward through the ice itself. Imagine that journey. A machine created on Earth lands on Enceladus beneath Saturn's pale light. Slowly, using nuclear power or thermal systems, it begins melting downward through kilometers of frozen crust. Above it lies the silent surface. Below it waits an alien ocean untouched for perhaps billions of years. No human has ever attempted anything remotely like that, and yet scientists are seriously discussing it because Enceladus has become impossible to ignore. Even space agencies outside NASA are becoming involved. The European Space Agency continues studying concepts for future icy moon missions. Japan's space agency has explored plume sampling proposals. Private scientific initiatives have even emerged, including the ambitious breakthrough Enceladus concept, funded partly through private investment. That alone says something extraordinary. Humanity is beginning to organize around the possibility that alien life may exist beneath Saturn's ice. For most of history, searching for life beyond Earth belonged to philosophy and imagination. Today it belongs to engineering teams, planetary scientists, chemists, and mission designers. The search is becoming real, and perhaps the most fascinating aspect is how quickly priorities changed. 2 decades ago, Enceladus barely mattered scientifically. Now it competes for the highest priority missions in astrobiology. That transformation happened because of evidence, not speculation. Evidence of water, evidence of heat, evidence of chemistry, evidence of hydrothermal activity, evidence of long-term stability. The moon earned humanity's attention, and yet every mission proposal faces the same haunting challenge. What happens if we actually find life? Because discovering alien biology would not simply answer a scientific question, it would change civilization itself. Part 17, the nuclear ice mole. Of all the mission concepts proposed for Enceladus, none sounds more like pure science fiction than the nuclear ice mole. And yet scientists are genuinely trying to build it. The idea begins with a terrifying problem. Even though Enceladus sprays ocean material into space, plume flybys may never provide definitive proof of life. Molecules can be altered during eruption. Radiation can damage samples. Biological signatures may be diluted or fragmented. To truly investigate the moon, humanity may eventually need direct access to the subsurface ocean itself. But the ocean is buried beneath kilometers of ice. Drilling conventionally through that much frozen crust on another world is almost impossible. Mechanical drills could jam, break, or freeze. Communication delays make repairs difficult. The environment is hostile beyond anything humans have experienced. So scientists imagined something radical. Instead of drilling mechanically, why not melt downward? This is the concept behind cryobots and ice moles. The proposed machines would carry powerful heat sources, likely nuclear-powered systems, capable of slowly liquefying ice beneath them. Gravity and thermal pressure would allow the probe to descend deeper and deeper into the crust, creating a tunnel as it moved. Picture this carefully. A robotic explorer, no larger than a torpedo, lands on a frozen alien moon. Then, over months or years, it disappears beneath the surface permanently. Above it lies the frozen desert of Enceladus. Below it lies darkness, absolute darkness. No sunlight has ever touched the hidden ocean beneath Enceladus. That sea may have remained isolated since before complex life evolved on Earth. The water there exists beneath immense pressure, surrounded by black ice and heated only by the moon's internal energy. As the cryobot descends, sensors monitor temperature, chemistry, and structural changes in the ice. Layers within the crust might preserve records of geological history, trapped particles, or chemical gradients. Scientists hope the ice itself may contain pockets where primitive biological material accumulated over time. Then comes the most extraordinary possibility. Eventually, the machine reaches liquid water. Imagine the moment. After traveling billions of kilometers across the solar system and descending through alien ice, a human-built probe enters another ocean. The first extraterrestrial ocean humanity has ever directly explored. Some mission concepts go even further. Once the cryobot reaches the ocean, it could deploy a second robotic vehicle, a tiny autonomous submarine known as a hydrobot. Now imagine that scene, a submarine drifting silently through alien darkness beneath Saturn's ice. No stars visible, no surface visible. Only black water stretching endlessly around it. Its lights illuminate floating particles, mineral clouds, and perhaps hydrothermal vents rising from the seafloor. And maybe something alive. This possibility is why Enceladus generates such emotional intensity among scientists. Unlike Mars, where life may have disappeared billions of years ago, Enceladus may still possess active ecosystems right now. The ocean is not ancient and dry, it is alive with motion. And if microbes exist there, they may never have encountered sunlight, oxygen atmospheres, or surface ecosystems. Their biology could differ radically from Earth's life while still sharing fundamental chemistry. The implications are staggering. A second genesis, a second independent origin of life, another branch on the tree of biology. But there is also fear attached to these missions. Contamination. Scientists worry constantly about accidentally introducing Earth microbes into Enceladus's ocean. Even tiny contamination could compromise future discoveries forever. Planetary protection protocols are therefore becoming increasingly strict. Spacecraft must be sterilized extensively before launch. Humanity is preparing to enter an alien ocean while trying desperately not to infect it. That balance feels almost symbolic. We are explorers standing at the edge of another world, carrying both curiosity and danger. And the deeper scientists think about Enceladus, the more one possibility begins dominating every discussion. If life exists there, then life in the universe may be common. And that realization changes everything. Part 18. If we find life, humanity changes forever. Most scientific discoveries expand knowledge. Finding life beyond Earth would redefine existence itself. It is difficult to overstate how psychologically overwhelming such a discovery would be. Humanity has spent thousands of years asking whether we are alone. Religions, philosophers, poets, and scientists all confronted that question in different ways. Enceladus may finally answer it. Imagine the announcement. A future spacecraft analyzes plume material and detects unmistakable biological structures, repeating patterns, cellular membranes, complex organic systems behaving in ways chemistry alone cannot explain. Or perhaps a cryobot photographs microbial organisms drifting near hydrothermal vents beneath the ice. At that moment, human history divides into two eras. Before we knew life existed elsewhere, and after, the effects would ripple through every part of civilization. Science would change immediately. Biology would no longer describe only Earth life. Suddenly, researchers could compare two separate evolutionary histories. Scientists could finally determine whether life follows universal rules or whether Earth's biology is just one possibility among many. Religion would confront enormous questions as well. Some belief systems would adapt easily, viewing alien life as part of creation. Others might struggle with the implications. Philosophers would debate consciousness, uniqueness, and humanity's place in existence. But perhaps the biggest change would be emotional. For the first time, Earth would stop feeling cosmically lonely. Right now, every living thing humans have ever known belongs to a single biological family tree. Every plant, animal, fungus, and bacterium on Earth shares common ancestry. Life emerged once, at least as far as we know, but if Enceladus hosts independent life, then biology is not unique. Nature created it twice in one solar system. That realization would transform our understanding of the universe, because if life emerged independently on both Earth and Enceladus, then the galaxy may be filled with hidden ecosystems, billions of planets, trillions of moons, countless oceans beneath ice. The universe may not be dead at all. It may be overflowing with biology hidden in places humanity never expected. This idea also affects the famous Fermi paradox, the question of why humanity has not yet encountered alien civilizations despite the vast size of the universe. Perhaps intelligent civilizations are rare, but microbial life may be common. The cosmos could contain oceans filled with primitive ecosystems, while advanced intelligence remains extraordinarily unusual. Enceladus may represent the beginning of that realization, and yet the discovery of alien life would also create fear. Because once humanity confirms biology exists elsewhere, we immediately face another question. How different can life become? Would Enceladus organisms use DNA like Earth life? Would they rely on amino acids? Would they metabolize energy similarly? Or would they reveal entirely new forms of chemistry? Scientists desperately want those answers because they would tell us whether life follows universal biological laws or whether evolution can generate radically different solutions. The discovery would also change space exploration priorities permanently. Governments would pour resources into astrobiology. Missions to icy moons would accelerate. Europa, Titan, and distant exoplanets would become even more important. Humanity would no longer search for life abstractly. We would know it exists. That certainty would reshape civilization psychologically. Children would grow up knowing Earth is not the only living world. Artists, writers, filmmakers, and philosophers would reinterpret humanity's role in the cosmos. The night sky itself would feel different, and perhaps the strangest emotional consequence would be humility, because finding life beneath Saturn's ice would remind humanity of something profound. We are not the center of creation. We are part of something much larger, and yet even as scientists dream about discovering life, another darker possibility remains. What if Enceladus has everything necessary for biology and still remains sterile? Part 19. The terrifying possibility that nothing is there. Enceladus may contain water, it may contain energy, it may contain chemistry, it may contain hydrothermal vents, and yet despite all of that, the ocean beneath the ice may still be empty. That possibility frightens scientists almost as much as finding life excites them, because if Enceladus truly possesses all the ingredients required for biology and still failed to produce life, then something about life's origin may be far rarer than humanity hopes. This idea connects to one of the deepest mysteries in science. How difficult is it for life to begin? On Earth, biology appeared surprisingly early after the planet cooled. Fossil evidence suggests life emerged relatively quickly on geological timescales. That fact encourages optimism. Many scientists interpret Earth's rapid biological emergence as evidence that life forms easily under the right conditions. But Earth may not represent the full story. Perhaps hidden factors mattered. Maybe certain chemical pathways are extraordinarily improbable. Maybe life requires environmental conditions more delicate than we realize. Maybe Earth experienced a series of rare accidents that Enceladus never did. If that is true, then Enceladus becomes something haunting, a world standing on the edge of biology, but never crossing into it. Imagine an ocean existing for millions of years beneath the ice. Hydrothermal vents release chemicals continuously. Organic molecules drift through dark waters. Energy flows, reactions occur, but nothing ever becomes alive. No self-replicating systems, no metabolism, no evolution. Just chemistry endlessly approaching biology without reaching it. That possibility touches the heart of the rare Earth hypothesis, the idea that complex life may be extraordinarily uncommon in the universe, despite habitable environments existing widely. Perhaps habitable worlds are common. Perhaps living worlds are rare. Enceladus may help humanity distinguish between those possibilities. If future missions explore the moon thoroughly and discover no evidence of life despite ideal conditions, scientists would face difficult conclusions. It might mean the transition from chemistry to biology requires events so unlikely that even habitable oceans often remain sterile forever. That thought creates existential loneliness on a cosmic scale, because it would imply Earth may truly be exceptional, a singular accident in a mostly silent universe. And there is another unsettling possibility. What if life existed on Enceladus once, but died? Perhaps the ocean changed chemically. Perhaps hydrothermal activity weakened temporarily. Perhaps environmental instability destroyed emerging ecosystems before they could evolve complexity. If so, Enceladus may preserve evidence of a failed biosphere, a dead second genesis. Imagine future probes descending into the ocean and finding fossilized microbial mats near ancient vents, evidence that biology briefly appeared before extinction erased it. That would be emotionally devastating and scientifically fascinating simultaneously, because it would prove life can emerge beyond Earth while also demonstrating how fragile biology truly is. Enceladus therefore represents more than a search for alien organisms. It is a test of cosmic biology itself, a test of whether life naturally fills the universe whenever conditions allow, or whether existence is far more fragile and improbable than humans want to believe. The moon forces humanity to confront both hope and fear. Hope that life may be everywhere, fear that life may be extraordinarily rare, and until we return, both possibilities remain alive, hidden beneath the ice, waiting. Part 20. Beneath the Ice. Tonight, somewhere beyond Earth's skies, beyond Mars, beyond Jupiter, far out in the cold kingdom of Saturn, Enceladus continues orbiting silently through darkness. From a distance, it still looks harmless, a small white moon reflecting sunlight, a frozen world surrounded by rings. But beneath that quiet surface lies one of the greatest mysteries humanity has ever encountered. An ocean, not a lake. not a pocket of meltwater, an entire hidden sea stretching beneath kilometers of ice. Right now, Saturn's gravity continues squeezing the moon gently during every orbit. Deep below the crust, heat rises from the rocky interior. Water moves through mineral-rich channels. Hydrothermal vents may glow faintly on the seafloor. And somewhere within that darkness, chemistry continues evolving. Perhaps nothing lives there. Perhaps the ocean is sterile. Perhaps Enceladus represents a beautiful but empty experiment in planetary habitability. But perhaps not. Perhaps beneath the ice, microscopic organisms drift through warm currents surrounding hydrothermal vents. Perhaps alien cells consume hydrogen and release methane into the ocean. Perhaps entire microbial ecosystems have existed there longer than human civilization has existed on Earth. If that is true, then life did not emerge once in the solar system. It emerged twice, and if it happened twice here, then it may have happened countless times across the galaxy. That realization changes the stars forever. Every distant moon becomes more interesting. Every frozen world becomes more mysterious. The universe stops feeling empty. Enceladus taught humanity something extraordinary. Life may not need sunlight, continents, blue skies, or Earth-like planets. It may survive in hidden oceans beneath frozen shells orbiting giant planets in deep space. The cosmos may be filled with invisible biospheres no telescope can easily see. And perhaps the strangest part of all this is how close we already came. Cassini flew through the plumes. Humanity touched particles from an alien ocean. We may have already held pieces of another living world inside our instruments without fully understanding what we found. That thought is both thrilling and haunting, because the answer may already exist somewhere inside old data waiting for future scientists to recognize it. Sooner or later, humanity will return. New spacecraft will fly through the plumes again. Landers may touch the ice. Cryobots may descend into darkness. Submarines may one day swim through extraterrestrial oceans. And when that moment finally comes, when human technology enters the hidden sea beneath Enceladus, we may discover something that changes civilization forever, not monsters, not intelligent aliens, but something far more important. Proof that biology is not unique to Earth. Proof that the universe learned how to live more than once. Until then, Enceladus continues circling Saturn in silence. A frozen moon hiding a dark ocean, an ocean hiding chemistry, and perhaps an ocean hiding life.